Okay, so welcome back. Now we're going to do a couple of more examples of composite function taking the derivative of it. The first one gives us sine cubed x, so now we're going to apply this to trigonometric functions. Okay, so again, understand that this cube is sine x quantity cubed, right? So this is a power function, or yeah, I guess you could call it a power function. And so again, we have the outside function is a power function, inside function is a trigonometric function. So if we were going to take f prime of x, again we take the derivative of the outside function. Now notice that we're moving from the outside function to the inside function. So actually, one thing I want to mention is that you could do this for composite functions of three functions that are composed, 4 more. So a couple things to keep in mind. We, one, are always moving from the outside function to the inside function. And notice also that the number of parts we have at the end, the number of parts or number of factors that we have in our product, okay? So, or parts would probably be a better word. So when you have 2 composed functions, you have 2 parts to your final answer. If you have 3 composed functions, you're going to have 3, and so on. Okay, so again, something to keep in mind. So f prime of x, the outside function is a power function, so we're going to drop the 3 down, and then we're going to rewrite this as sine squared x, because we reduced the power by 1, we just left the function as is, the inside function stays the same. Now we're going to multiply this by the derivative of the inside function, which is sine, so the derivative of sine is cosine x. And so now we simplify it, and this is really just becomes 3, and again, order doesn't matter, but 3 cosine x sine squared x. Okay? And we're done. So now let's look at the next one. Now the next one wants us to find the equation of a line tangent to the graph of h of x is equal to 1 over the quantity 3x minus 1, or excuse me, 3x minus 5 quantity squared at x equals 2. So we want to find the slope of the tangent line on this function at x equals 2. So again, well, the first thing is we want to find what point we're dealing with. So this is going to be 2, comma, well, at 2, what do we get? Well, we'll get a 1, right? So we get 6 minus 5 is 1, 1 squared is 1, 1 divided by 1 is 1. So there's our point. Now we just need the derivative to find the slope, right? We need the slope. So m equals what? H prime of 2. Well, in this case here, I'm going to look at this as, this whole thing, I'm going to look at 3x minus 5 to the negative 2 power, right? So again, I'm rewriting h of x to equal 3x minus 5 to the negative 2nd power. So I can use the power rule, right? Make it easy on yourself. So now I'm going to write it as the derivative of the outside function, so that's going to be negative 2 times 3x minus 5. Notice I leave the inside function alone, and then I'm going to reduce it by 1, which is going to give me negative 3, and now I'm going to multiply by the derivative of the inside function, which is just 3. And so now what I'm going to do is I'm going to multiply the coefficient factors here, so I'm going to get negative 6 divided by, because now this is a negative power, so I'm going to bring it down to the denominator to make it positive, and so I get the quantity 3x minus 5 cubed. Okay, now I'm going to evaluate this at 2, right? So I'm going to evaluate this at 2 to get the slope. So this is going to give me negative 6 over, well, again, this is going to be 6 minus 1, which is 1. 1 cubed is 1. And I get negative 6 as the slope. And so now, this is where just algebra, right? So now it's just y equals mx plus b. And of course, y is 1. The slope is -6. X is 2. And we're looking for the y-intercept. So this is going to be -12. So if I add -12 to both sides, I get 13. So b is equal to 13. And I'm done. So the equation of the tangent line at this point on this graph is y equals -6x plus 13. And I'm done. That's it. Have a great day. Practice.